build a model that works in 3D. This is just a quick introduction of my method as well as what static and continual learning is. So all of us here know, but yeah, I just want to have this slide. So basically, when we have static method, so we train the model once, and then it will be stuck, so it is locked, and then there is no updation of this model. So it's basically doesn't learn new classes or and fails in new environment. So in continual learning, so we have initial stages of learning. So for example, here sofa, table, and chair. And then once the new category comes in, we want to learn that category as well. So it's a kind of loop which learns the new category, for example, cabinet in this example. And similarly, when we move forward, it should learn the new classes as well. But when we have the continuous learning, but the challenge, there are some challenges in deployment. For example, when a new category observed, it only comes with few examples. Because human annotation is expensive and collecting the data requires heavy annotation as well as it's expensive. So it makes sense to learn from few examples. So basically, task 0 or the base learning process has like lot of data, and then when new classes comes in, which is in a few examples. So this is kind of whole pipeline that is there. So base classes means we already have some kind of foundation model, and when we go forward and deploy that model, and when new classes comes in, it should learn from the few examples. So this is kind of a typical incremental setup looks like. So in initial stage, we have a lot of base data, which large amount of annotated examples. But when the novel classes comes in, it only comes with the few examples. So this is kind of how these incremental few shot setup looks like. So based on that, so what we have seen that there are some method that works on incremental few shot setup for 3D, but what they usually do is when the few shot labels comes in, so they kind of create a prototype based on those labels only, and those are not generalizable and leads to poor performance on these novel classes. So then what we found is, these methods actually ignores this background context. For example, here, so this is a cabinet, but this is completely ignored by those methods. And we saw that if we use this information somehow, so that we can boost up this or enhance this prototype for the better results. So that's what our method is about. So what we did basically is we extracted, so given the base scene, so because base has a lot of data, so we wanted to use this large amount of data to build a better future prototype. So what we did is we extracted this background objects from this base scene, and then build this, store the information in a memory, and then you will use this information. So for that, we use class agnostic model, so which basically produce instance mask for the scene. It doesn't produce any class label for those instance mask, and it's basically just a binary mask for each object. And we'll pass this instance mask to a 3D encoder to build the prototype for this object, and those will be saved in this instance prototype bank, which will be used for learning new classes. So one also thing I want to mention is because we use this prototype bank and not build the cluster, class specific cluster, because in continual learning setting, we assume that we don't know anything about future. So we don't know anything, like we don't know the names of the class which will occur in the future, or we don't know that how those gonna come in. So that's why we can't build class specific prototype. So those is so that's why we went with instance prototype bank, which is class agnostic memory bank. So this is like overview of the method. So there are like basically 3 stages: base training, then scene contextualization, and incremental class registration. So there are like these 3 stages. So of which, so in base training is just the standard 3D encoder training, which will be trained on large amount of 3D data. and which only have this base classes labeled, and others are like considered as a background. So this is standard gradient optimization. After this, we'll move to scene contextualization, which is the second stage, where I will use the same data from the base stage and create this instance prototype bank. So which is basically just taking the instance mask, feeding it to encoder, and building this instance prototype bank. So this will be stored and then used for the next task. So in incremental registration phase, so after getting the few shot label, after getting the few shot label, we'll basically use this supports. So we'll build the so this is called support set, and we'll use this support set to query as a query to retrieve some of the prototype from the instance bank. So which will be kind of pulled up. So which just the cosine similarity or something like some similar function which can be used to pull up this uh, prototype from the instance bank, and will add those prototype along with this support set, which is our enhanced prototype for that particular class. And so once we have this enhanced prototype, we can just use this with this previous prototype for the base class and learn these novel classes. So these are the experiment details. So we actually tested this method on two data set, through 3D data set, ScanNet and S3DIS. For the backbone, we use a DGCNN. So for the class agnostic model was segment 3D. So we tried with k is equal to 5 and 1 k shot. So there are like total 4 classes. One is base and 3 novel classes. For the evaluation metric, we have mean IOU, and for the base we have mean IOU base. Then now for novel there is novel. So harmonic mean is actually used to as actually this mean IO is biased toward base classes because there are like multiple base classes compared with novel. So this harmonic mean actually kind of this remove the bias and shows the actual results. So we also have incremental mean IOU, which basically tell us how much information has been there for throughout the classes. And then we also have forgetting percentage point, which basically just measure the forgetting of the first task from the first to last, and which is lower is the better. So so main column to look at is novel classes, because we are mainly focusing on the novel class learning, and base is just the same. For example, so we so this is GW, which is our like strongest baseline. So we see that when we compare with those methods, our methods works better, and it improves quite a lot for the novel classes. So base is kind of around same, because it's the same base that is used for the both method. Similarly, when we look at this, when there is only k is equal to 1, it also shows the similar performance. So this is for STDR dataset, which also shows the similar effect. It improves for the novel classes in both the settings. So this is performance across the task. We see that it also throughout the task progression, it stay consistent and shows better performance than other methods. So we also did some ablation. So this CPR is oh yeah, so I forgot to mention so this is contextual prototype retrieval, so which basically the cosine similarity metric. This contribute to over this GW method. Similarly, we also have AP, which also improve the results further. Yep. So this is what I have. Thank you, guys. Yep.